These are the solutions to activity 4. So the first question, when we have 2.5 moles of P4 and 10 moles of O2 reacting by the below reaction, how many moles of our product can form? Well, we have to think of this question here without, in this case, being directly told. We have to consider which of the two reactants is a limiting reactant. So what I'm going to think about is, what if all of this P4 converts into product? For every 1 mole of P4, we'd get 1 mole of P4O10. So this would produce 2.5 moles of P4O10 if all of it reacted with an excess of oxygen. And then for the O2, if all of this reacts and produce P4O10, for every 5 moles of O2, we get 1 mole of P4O10. So if I'm trying to calculate the number of moles of P4O10 from 10 moles of water, 10 moles of O2, for every 5 moles of O2 that react, we produce 1 mole of P4O10. So I'm only going to get 2 moles of P4O10 when I consume all of the oxygen. So I get the 2 moles of P4O10 and I run out of O2. To get the 2.5 moles of P4O10 with the excess P4, I'd have to have more oxygen available than what we have present in this reaction. So the most amount of product we can get here is 2 moles. And then P4 is our excess reactant. And then O2 is our limiting reactant. The limiting reactant is one that's limiting of how much product we get formed in the reaction. Second question, how many grams of HCl are produced when 1.23 grams of titanium tetrachloride, titanium 4 chloride react with an excess of water according to this reaction below? So we have another stoichiometry problem, but I don't have a limiting reactant problem because I know I have an excess of this. I know I have 1.23 grams of the titanium chloride, so I know this is my limiting reactant. I'm clearly told water is the excess reactant here. So the number of grams of HCl we're going to produce in this reaction, I'm going to start with 1.23 grams of titanium chloride. Then I need to use the molar mass of TiCl4. So I need to take 47.88 for titanium plus 35.45 times 4. That gives me 189.68. Then for every 1 mole of TiCl4 that reacts, we produce 4 moles of HCl. And then I need to use the molar mass of HCl. 1 mole of HCl is 36.46 grams. And so we do the math here. 1.23 divided by 189.68 times 4 times 36.46 gives me 0.946. So that's the quantity of HCl that should be produced in this reaction. Next question, I have 2.25 moles of TiCl4, same reaction as before. 5 moles of water react by the below reaction. Which reactant is present in excess and how much of it remains? Okay, so given moles here, if we're given grams, this problem isn't really any harder if we're given grams instead of moles. If we're given grams here instead of moles, just convert to moles, or think about how much of one reactant you need to react with the other. With moles, it's just a little bit maybe easier to be able to see for every 1 TiCl4, we need 2 waters to be present. So this is going to require us to have 4.50 moles of water, and I have 5 moles of water. So in order for 2.25 moles of TiCl4 to react, so if I have this at 2.25, this at 5.00, think of this equation here. If we want to set up a BCA chart, if this goes to 0, if this is our limiting reactant, then X would be equal to 2.25 moles. And so 5 minus 2 times 2.25 leaves behind half a mole of water. And so water is going to be our excess reactant because it's the one that we have some leftover quantity when all of the other reactant completely reacts. So we lose titanium 4 chloride down to 0, and then water remains in excess with a half a mole remaining. So we got half a mole of water remaining. So water is our excess reactant, half a mole that remains. Now let's just double check real quick. What if we were to consume, what if we made a mistake, or what if we want to just double check what would happen if all the water were consumed? How much TiCl4 would be required? Well, if all the water reacts, the amount of the titanium chloride that would have to react with it would be 5 moles of water, and times for every 2 moles of water, we need to react with it 1 mole of TiCl4. That would be 2.50 moles of TiCl4, and we only have 2.25 moles. So that's more than what we have available. So you can't react more than the given quantity. So water cannot be the limiting reactant, therefore it has to be the excess reactant. So let's say we have 2 moles of Fe2O3, 6.5 moles of carbon are reacted. The reaction yield is 3.64 moles of iron. What's the percent yield of the reaction? So the idea here would be we have 2 moles here. You want to set up a BCA chart, that's fine. If I'm given moles, sometimes a BCA chart is a little bit easier to construct. Sometimes it's also easier when I have room to write. But the reaction is balanced. So I have 2 irons. I have 1, 2, 3 oxygens, 1, 2, 3 oxygens, 3 carbons, 3 carbons. So reaction's balanced. Just kind of doing a quick double check there. Now, the way I can set up my BCA chart is to change the amount. The X is just like the ratio. For every 1 Fe2O3 that we lose, we have to lose 3 carbons. So I'm just using my coefficients in front of the reaction. I'm not, I can also write in the products here in terms of them initially being 0. Reactants usually, there's none of them present to begin with. So we only have the reactants present initially. And so we would have 2x, 3x after the reaction. And then one of these two here should be down to 0. The question is which one's the limiting reactant? And same type of problem as before. Now, if we're not sure, just set one of them to 0. I'm going to set the wrong one to 0 real quick. I can tell this one's wrong because I'm going to need more Fe2O3 than I have available. If this is 0, what's x equal to? X would be equal to 6.5 divided by 3, which is over 2. So 6.5 divided by 3 is 2.17. 2 minus 2.17 would be negative. And so we can't have that, of course. And so that limiting reactant must be the iron oxide. So that's going to go to 0. X is going to be equal to 2 moles. And so 3 times 2 is 6. Subtracted off 6.5, I have half a mole of carbon remaining. And I'm forming 4.00 moles. Writing. So 2 times x, where x is 2. So that's 4.00 moles of iron form. So this is our theoretical yield. The theoretical yield is the yield that you get from stoichiometry, the yield you're getting from writing out and balancing these reactions. That's our stoichiometric yield, is another way of thinking of the theoretical yield. This is the maximum yield we should ever get. And so we only got 3.64 moles. So our percent yield is just equal to 3.64 moles over 4.00 moles times 100%. So that's 91% yield. I'm just showing this chart here. You get this on exam, so students, you can use this information to help solve problems of solubility and predicting when we have things called metathesis reactions taking place. So you can refer back to this slide as needed for the next problems. So we have KClO4 readily dissolves in water. Now, something not on that previous chart is that all ionic compounds containing alkali and NH4 plus cations are water soluble. So anytime you see potassium, you know the compound's water soluble. So I see K plus. I know the counter ion's KClO4 minus. This is perchlorate ion. And so when KClO4 hits water, it ionizes because it's an ionic compound of ions, and it's water soluble. All ionic compounds that are water soluble ionize, meaning this is going to form K plus and ClO4 minus in water. Then all of our polyatomic ions remain intact. They're not going to break apart. This thing doesn't fall apart into oxide and chloride ions. This is a nonsensical answer. That wouldn't even be balanced anyways. It would have to, if it did fall apart, it would have to fall apart into oxide and like chlorine plus cation, which makes really no sense. So this ion here is stable, stays intact. So we get K plus and ClO4 minus ions. Think about the name. The compound's going to dissociate into the name that we gave it in terms of its ions from chapter 2. Which compound here is insoluble in water? So if you go back to the solubility chart, for chloride, bromide, iodide, also sulfate, so these ions here, one of the exceptions for these ions is this ion, Hg2, 2+. Generally, compounds with these ions are water soluble. So the exception here is insoluble. So you pair Hg2, 2+. This is that weird ion we mentioned in chapter 2 and naming briefly. But Hg2, 2+, paired up with iodide would be Hg2I2. So you need 2 of the I minuses to balance the 2+. And if you were to pair this with sulfate, it would be Hg2SO4. So these compounds here are insoluble in water. So which compound's insoluble? Hg2I2, this is definitely insoluble in water. Now, if you look on the chart, for chloride, bromide, iodide, there's 2 other exceptions. That's silver plus and lead 2+. Sulfate has a few different ions. It has the mercury 1 cation. It also has the lead ion, but not silver. But let's not get too distracted by sulfate here. But the idea of the chloride, bromide, iodide, sulfate is that mercury 1 is the exception. So mercury 1 is this ion where we have 2 mercuries bonded together with a net positive charge on both. It's kind of like peroxide. It's like a molecular cation, but of metal atoms. It's the only one example of this that we see here in general chemistry. And it's interesting that it forms these insoluble compounds with these 4 anions, chloride, bromide, iodide, sulfate. But then it's also interesting to note that it has that mercury can form an ordinary 2+ cation. So Hg2+ is mercury 2, just as you would expect any transition metal with its charge of 2+, it's mercury 2. That mercury 2 is not an exception that's listed for these ions. So therefore, Hg2Cl2 is water soluble. So it's important to note that the insoluble exception is insoluble in water, but then that mercury has another common ion that would be soluble. And these compounds are actually very common. You know, like you can buy HgCl2 and you can buy Hg2Cl2. These are very common compounds. So this compound here is soluble, not one of the exceptions, and this one here is insoluble. So only Hg2I2 of these choices is insoluble in water. Now mercury is weird, forms 2 common ions, mercury 1, which is that Hg2 2+ ion, and then the ordinary mercury 2+, mercury 2. Silver and lead, those are only forming 1 common cation. So if you're wondering, does silver and lead have this issue? They only form 1 common cation. There's another question later that'll ask us to write some formulas of compounds that are insoluble, but we could be writing and noting that AgI, PbI2 are insoluble in water, and then those metals don't have any other common cation that would be soluble, like mercury does. Which compound below is soluble in water? Anything with potassium is water soluble. Calcium carbonate. Carbonates are mostly insoluble. The only exceptions for carbonate are the alkalis and NH4+ cations. So this compound here is insoluble. One of bromide's exceptions is silver plus. So the exceptions for bromide are insoluble. So AgBr is insoluble. Hydroxides are mostly insoluble. The only exceptions for hydroxide are alkali, the heavy alkaline, which are these, and NH4 plus. You can look back on the chart, but these are the only soluble exceptions for hydroxide. All the others are insoluble. So these three here are insoluble in water. Methanol is miscible with water. What solute particles exist in an aqueous solution of methanol? One of the keys with molecular compounds is we have to kind of think, is the molecular compound an acid or is it a base? And the acid thought should be, do we name it as being an acid? And if the answer is no, then it's not an acid. If you can name the thing for being something acid, then you would call it an acid and it would behave as some kind of acid in water. So, excuse me. So methanol, not being an acid, not being named something acid, is definitely not an acid. And then in terms of it being a base, what are bases? Well, bases are things that create hydroxide ion in water. Sometimes we look at this thing here and we see this group here and say, well, that's the thing we call a base. Can this thing fall off to make hydroxide ion? The answer is no, it doesn't fall off of methanol into water. So methanol is not a base either. The only molecular compound that we can really see as being a base here from chapter 4, the only one I would expect that you recognize is NH3, or the case of anything where we have three things bonded to a nitrogen atom where we have a lone pair on nitrogen. Now, these are kind of hard to spot, without knowing how to draw Lewis structures, but this is really what makes something a base. Lone pair on nitrogen, three things attached to it like hydrogen, methyl groups, but this is really our main prototype for a molecular compound that's a base. So if you don't see NH3, you see some other compound, not a base. So that what that's telling us is the only particles that should be present when methanol dissolves and mixes in water is the methanol molecule itself, because it's a non-electrolyte. So we can divide compounds into ionic compounds versus molecular. If an ionic compound's water soluble, it has to ionize. That's the way it dissolves in water. And then if it's a molecular compound, it either ionizes by being an acid, it either ionizes with water through its reaction like ammonia does by being a base, or it doesn't ionize at all like methanol and most other molecular compounds that aren't named acids or bases do. What solute particles exist in an aqueous solution of acetic acid? So here we know acetic acid's an acid because of its name. We can take that for granted. And so the way this would kind of go with recognizing an acid is recognizing some underlying ion that we know how to name, that's acetate. H plus added onto it is that acetate ion in its acid form. And so when this thing dissolves in water, what happens is we get a partial equilibrium where it forms some H plus ions and then some C2H3O2 minus ions, this being the acetate ion. So we're getting some formation into these ions here. We get less than 100% yield because this is not one of our 7 strong acids. So we think, is it one of the 7 strong acids? 7 strong acids being HCl, HBr, HI, HNO3, HClO3, HClO4, and then H2SO4, the first hydrogen coming off. Notice some exceptions. We don't see HF. We don't see any acids. We don't see any acids of ions that end in ITE. These are only the ATE acids, and these aren't all the ATE acids. These are just some of them. Like we don't see phosphoric acid on this list. So acetic acid's on this list, so therefore it must be a weak acid. So the implication here is that this must be a weak acid by simple inference, by it not being one of the 7 strong acids. So what that means is we get mostly still acetic acid molecules, but we do get some formation to acetate and H plus ion. Okay, we don't get complete formation. This would be the answer if it were a strong acid, but it's not a strong acid. So answer C is wrong. And then A is what we would get if the molecule is a non-electrolyte, but it's an acid, so acetic acid is not a non-electrolyte. And then answer D is what we would have if the compound didn't dissolve or mix in water at all. So if it were insoluble or didn't mix with water, it would be answer D. But our acids are going to mix in water because they're going to dissociate. Just a matter of how much they're going to dissociate. And our bases are going to mix in water. And then for a lot of molecular compounds, we don't always guess or know solubility trends. You'll see some more of those when you look at solutions in more detail in Chapter 13 and Chem 1220. Question 10, which below is not a strong acid? Kind of just went over the 7 strong acids. So HF is not one of the 7 strong. You would think it might be because 3 of the 4 hydrohalic acids are strong acids, but HF is not. Now, HF is still extremely hazardous to work with. What ends up happening is that you get such a strong attachment of the negative and the positive charges that form on HF that the hydrogen becomes kind of locked into fluorine. That bond becomes really strong as a result. And so that's kind of why HF, you'll talk maybe a little bit about why it's not a strong acid in chapter 16 later as well. But HF, not one of the 7 strong acids. Question 11, what solute particles exist for this acid here, which is a strong acid? So this is going to be all nitrate and H plus ions, so HNO3, and water is going to be all H plus and nitrate ions to 100% completion because this is a strong acid, strong electrolyte, completely ionizes into its ionic products. Question 12, what compound forms which compound forms a basic solution when dissolved in water? So we have methanol doesn't do this because it's not an electrolyte. This is insoluble, so this doesn't do it. So that's insoluble. So it's hard for something that doesn't dissolve in water to do anything in water. So no reaction with copper hydroxide in water, so it doesn't change or make water basic. But ammonia does. Ammonia reacts with water. The way this works is you get a partial equilibrium where you take an H plus off of water. So you take an H plus off of water, leave behind hydroxide ion. So you form NH4 plus hydroxide ion. And so making hydroxide ion, anything that makes hydroxide a base, you make a partial amount of the base, therefore it's a weak. So this is a weak electrolyte, weak base. So ammonia does that. And some last examples for the activity. What's a weak, give an example of a weak diprotic acid. You can give a couple H2SO3. That's not one of the 7 strong acids. You could go H2CO3. Those are probably the 2 main examples I can think of weak diprotic acids. A strong monoprotic acid. This is 7 of the 6 are monoprotic acids that are strong acids, so like HCl, HBr. So having one H plus to dissociate is what makes something be a strong acid. A strong base is a water-soluble ionic compound with hydroxide ion. So examples could be things like KOH, sodium hydroxide, calcium hydroxide, ammonium hydroxide. So these are going to be the water-soluble hydroxide-containing salts. A weak base, only one real example that we see and use a lot in this chapter, and that's ammonia. And then the last question, just writing some reactions here for acid-base reactions. Full molecular would be HCl, aqueous, dissolved in water, sodium hydroxide is water-soluble, so that's AQ. So this reacts in water to form NaCl, water-soluble. And then water is the liquid, that's the solvent, so that's water liquid. If we want to ionize this reaction, we go H plus Cl minus. Anything plus is aqueous. I'm going to save the trouble of writing a bunch of AQs. And then water doesn't dissociate, so it's just water liquid. So then our net change, we can cancel out our spectator ions. So let's cancel out whatever ions are exactly the same in both sides. So that'd be chloride and then sodium. And so our net ionic would be H plus OH minus, forming water liquid. So this is our net ionic, this is our full ionic, and this is our full molecular. And by molecular, we mean like a molecular reaction is kind of just writing the compounds that we know are strong electrolytes as if they were still molecular or intact, even though we know that HCl-AQ is really H plus and Cl minus. So we're dissociating here our strong electrolyte. So anything that's a strong electrolyte is dissociated into the full ionic reaction. Then we just cancel out our spectators. The spectator ions, or the unchanged ion for this reaction, would be sodium plus and chloride ions. They don't disappear, they're just canceled out for the net change. And if we want to include the AQ tags, we can do that for all the charged substances. I just was neglecting them for brevity. Metathesis reaction between calcium chloride, CaCl2, and water, so that's AQ, plus K2CO3, also water soluble. Anything containing potassium is water soluble. That's not an exception for chlorine. And so the products here should be calcium carbonate, which is insoluble in water. That's what drives this reaction to actually take place. We have to get at least one solid gas or liquid on the product side in order to actually have this reaction take place. If I have AQ in all spots, then we're just mixing ions together and there's really no reaction taking place. Then the byproduct would be KCl, AQ. So let's balance this reaction real quick. I'm going to need 2 KCl's, and I think that should be good. And so then if I want to write the full ionic equation, I'm going to dissociate the strong electrolyte calcium chloride. So that'll be calcium 2 plus 2 chloride. And then K2 is also a strong electrolyte. So I can dissociate it into 2K pluses plus carbonate ion. Again, I'm neglecting to write AQs for all of these for just not wanting to clutter up the page more than I need to. Calcium carbonate solid, this is insoluble in water, so this is not a strong electrolyte. So when I'm thinking, is this a strong electrolyte? The answer is no. You have to be water soluble in order to dissociate. So I leave calcium carbonate intact, just like I left water intact. And so then we're going to form 2K plus 2Cl minus ions. And so then canceling out our spectator ions, K plus, Cl minus, identical form both sides. So the net change, think net ionic is just, well, what's the actual net reaction taking place here? That's calcium 2 plus aqueous plus carbonate ion 2 minus aqueous producing calcium carbonate solid. So that's that net ionic reaction or equation for that metathesis reaction. So metathesis is the exchange of metal atoms between their anions and seeing if we form something like an insoluble compound, or like I mentioned, something like water, or something gaseous even, something that floats away from the reaction that doesn't allow the reactants to reform. Again, remember, if you get aqueous in all 4 spots, if you have 2 aqueous compounds forming 2 aqueous compounds, pretty hard to envision a reaction actually took place there. So we got to get something that actually allows there to be a net change to take place during the course of the reaction. That's where metathesis and precipitation reactions kind of come into play. All right, well, that's activity 4. Have a great week, everybody.